I'm so tired and hungry. I knew I shouldn't have stayed up watching One Piece last night. Oh no. I have a physics test today, and I don't know anything about thermodynamics or energy. But I'm so hungry. But I'm gonna fail the test. Ah!
Fear not, your friendly neighborhood physicist to the rescue. Do you know that we can actually learn about physics and cook your breakfast at the same time?
What? No, we can't. I was gonna cook potatoes. You can't learn about physics and potatoes at the same time. That's ridiculous. The only thing physics and potatoes have in common is that they both start with P and end with S. And you know what PS rhymes with? B.
Hey, this is a family-friendly physics show.
This is taking a while. I wish it would just boil instantly. Wait, why doesn't it boil instantly?
Well, it has to do with the temperature difference between the stove and the pot of water. So if we just put an empty metal pot on the stove, it would actually heat up fairly quickly. But because we put a lot of water into it, the process is much slower.
The reason why the empty pot heats up faster is because of the way that heat is being transmitted directly from the stovetop to the pot itself. This is called conduction. But not all materials are equally good at conducting. Metal is a great conductor, which is why we use it for pots and pans. But sometimes it's a little too good, which is why people typically prefer to use wooden spoons over metal spoons when they're cooking. Another way heat is transferred is called convection. When a fluid, in this case water, is heated up, a very interesting pattern forms. The water at the bottom of the pot is closer to the heat source, which means it warms up faster than the water above it. As the water gets warmer, it expands and becomes less dense, rising from the bottom of the pot to the top. As the water cools, it falls back to the bottom of the pot and the whole process starts over again. This cycle, in its completion, forms what we call a convection current.
So this process, when a hot object shares its heat with a cold object until they reach equilibrium, is known as heat transfer.
And that's what's happening with the potato too, in a way, right? The heat of the water is transferring to the potato and cooking it.
Yes, exactly. So what happens when we put a cold or room temperature potato into a boiling pot of hot water is we create a temperature gradient, which is a temperature difference.
So the cooking of the potato is just a physical representation of the water trying to get back to equilibrium temperature with the stovetop.
Exactly. There are actually scientists who have tried to replicate this experiment in the lab, and what they've done is they've cooked potatoes at different temperatures, taken them out, done cross-sections, and then measured the width of the cooked part of the potato over time to find out that actually the cooked region of the potato increases with the square root of the cooking time.
Let's try it. I don't have a fancy temperature-controlled bath, but I do have more potatoes. Conveniently enough, our first potato just finished cooking. So let's cut this baby open and see what's inside. Well, it is just a regular cooked potato. Now let's cook a second potato for half the time and see what happens.
So what do you think?
I knew it would be different, but I didn't think the difference would be so dramatic, especially comparing it to a raw potato. But I think we should keep going because my hunger is increasing as a square root of the cooking time too. And another thing.
I think having just potatoes is a bit boring. Let's cook an egg too.
Sure, why not? I think that's an excellent idea.
Well then, let's get cracking. I cooked a hard-boiled egg yesterday for a snack, but I put it in the same bin as the other raw eggs. Now I don't know which is which.
Fear not! Physics to the rescue!
There's actually a very simple way to figure out which egg is raw and which egg isn't. Spin both eggs on a flat surface and stop them by placing a finger on each. When you lift your fingers, one egg will start moving again. That egg is the raw one.
That's so cool. But why does it happen?
Well, it's because of states of matter and also because of momentum. So a raw egg is all liquid on the inside and solid on the outside because of the shell, while a cooked egg is solid all the way through. So when we spin the eggs, after we try to stop them, the liquid on the inside of the eggs keeps on spinning because it has momentum, and that momentum carries the egg itself to keep on wobbling even after it's stopped. While a solid egg, it's solid all the way through because it's cooked, so it just stops when you stop it. So now that we know that this is the raw egg, what do you want to do with it?
Let's make a fried egg. It is Friday. Oh, wow. Now that it's spring, it really is getting hot. Any hotter, and we could probably ditch the pan and just fry it on the sidewalk.
Hey, yeah, that's true. You probably could. Have you ever wondered why, even though the sun is 92.93 millions of miles away, we can still feel the warmth of its rays? Like, we know that space is a vacuum, so convection and conduction don't work out there. Why do we still feel the warmth of the sun?
Because it's hot? Like really hot?
No. Because it's radiation. Radiation is another way that heat transfers. While conduction and convection both require materials or for things to be touching to transfer heat, radiation doesn't. Sunlight is a sort of an electromagnetic wave, or at least the sun's warmth is an electromagnetic wave, and that doesn't actually need materials to travel through.
Electromagnetic waves? That sounds complicated.
Well, it's really not. There are examples of electromagnetic waves all around us. For example, radio waves or visible light. It's just that some electromagnetic waves are visible, like light, and some are invisible. And even those electromagnetic waves can travel through vacuums to get to us and spread warmth. And that's what radiation is, electromagnetic waves spreading warmth.
Well, it's not quite that hot outside yet, so let's just stick with the pan for now. I just hope that they turn out right this time. My fried eggs never turn out quite right. They always end up burned on the bottom and not quite as cooked as I'd like them to be on top. You got any physics tips for that?
Well, whenever I'm in doubt, I always use one resource.
Google!
Oh, look at this article.
Interesting. I never thought to put a little water in it while it's cooking. But I guess it makes sense because the steam would help the top part cook faster to keep up with the bottom part so that it doesn't burn.
Yeah, let's try it.
Wait. But how will we know when the pan is hot? I don't want to touch it, but if we put the egg in too early, it won't cook right.
Fear not. A lot of chefs use this trick to tell when the pan is hot enough.
Whoa. It's like magic. Why are the water droplets moving like that?
Usually there are 3 general states of matter. Do you know what they are?
Yeah, solid, liquid, and gas. Water is liquid, but the solid form would be ice, and the gas would be steam. The temperature at which water becomes ice is the melting or freezing point, and the temperature at which water becomes steam is the boiling point.
Exactly! When the pan is way above the boiling point of the water, the bottom part of the water droplets evaporates, and the steam insulates the water droplets from the heat. This is called the Leidenfrost effect, wherein water droplets move freely around on a layer of steam.
All right, time to find out if these people on the internet know what they're talking about.
Nutrition. Oh, wait. There's one more section of the test that I haven't even read up on. And we've already finished cooking. Friendly neighborhood physicist, do you know anything about the scientific method?
Why, yes, I do. Actually, I'll let you in on a little secret. While we were cooking, we were already doing the scientific method. So technically, by your definition, you are already a scientist.
Wait, what?
Yeah, so the scientific method is a way that physicists, biologists, chemists, and all other scientists use to explore observations and get answers to their questions. The steps are 1. Make an observation, 2. Ask a question, 3. Form a hypothesis, 4. Make a prediction, and 5. Test that prediction and hypothesis. So we kind of have already done it.
Wait. I think I know why you said we already did this.
My onions will never turn out quite right. They always end up burned on the bottom and not quite as cooked as I'd like them to be on top. You got any physics tips for that? Well, whenever I'm in doubt, I always use one resource. Google! Interesting. I never thought to put a little water in it while it's cooking. The steam would help the top part cook faster to keep up with the bottom part so that it doesn't burn. Yeah, let's try it.
Am I right?
This is excellent, my budding physicist. Who says we can't cook and learn physics at the same time? Let's dig in. Another cool physics tidbit for you. As we're sitting here eating, we're actually already converting different energies.
I think I remember learning that. Doesn't a chocolate chip cookie have more energy than a TNT?
Why, yes, that's correct. The egg we just cooked has around 72 calories. That's calorie with a big C. And the potato has around 110 calories, which together equals around 760,000 joules. Let's look at a chart that tells us how different objects compare.
Whoa. My breakfast has more energy than an asteroid traveling 30 kilometers per second? How is that even possible?
Well, it has to do with the timing of it all. Things like TNT convert their energy in a super tiny interval of time, which makes the conversion much more dramatic. This is when it explodes, right? Humans convert food to energy pretty slowly, so even if the energy is higher, you won't explode just by eating breakfast.
Well, if I exploded, I probably wouldn't have to take this test, but I do feel more prepared since you came. So, nice.
Well, I'm just here to help. It's my mission to spread the joy of physics around the world.
Thank you for teaching me about this stuff. I never knew there was so much physics in food.
Physics is everything.
Dance break?
Yes. Wait. Don't you have a test to get to?